All right. Thank you, everyone, for coming. So we're very, very happy today to have Lars van der Wense visiting us to give us our physics colloquium. So Lars has a master's in applied mathematics from Cambridge, also known as Part 3, and then went on to do his PhD studies at LMU Munich, where his thesis was on 229 thorium. And then he went on to a postdoc at Munich, and then a postdoc with us at JILA, working with Junier, where he continued his studies. Is currently a research group leader at JGU Mainz. And I think it's safe to say that he is one of the world's foremost experts in thorium-229, but as to why that's so interesting and exciting, I think I'll let him tell you that part of the story. So please, Lars.
Thank you very much, Ethan, for the kind introduction. Yeah, actually, it's my great pleasure and also an honor for me to be here the second time, because I had the opportunity already to give a presentation here back in 2019 in exactly the same place. So I guess most of you will probably remember my talk from 2019, so I decided to just skip the introduction and then jump right into the developments following up from 2019, which was a lot, so that will certainly fill my presentation. It's all about thorium-229, and yeah, the most important thing, actually, what has been going on since the last time when I was able to give this presentation here was that actually laser spectroscopy of this nuclear transition has been successful, with the most up-to-date and most accurate values of the spectroscopy coming from JILA. So that's exciting. And I would like to give a little bit of an historic overview of what has happened before that, what has led to this great success, and also now that we have achieved this laser spectroscopy, what can we do with it? So what are the future applications of this? So that's an outline of my talk. Yeah, I was kidding. So I will give a slight motivation. So there will be a little bit of introduction here. I will have some parts of historic developments, because this is also the parts where mostly I was involved in, and then jumping to this big, interesting part of laser spectroscopy before coming to the future applications, and what actually do we need to do still to achieve these future applications. So in particular, what we are currently developing in our group at the University of Mainz. So why thorium-229? There is a total number of known isotopes of about 3,300 something. The total number of known levels within these isotopes is somewhere at 175,000. And between these levels, we have transitions of about 270,000 known. But there is only one transition of these 270,000 that actually allows for direct nuclear laser excitation, and this is specifically this thorium-229 metastable excited state that we are looking at here. And for what reason? It's actually the lowest nuclear excited state of all isotopes known to date, with an energy in the range of something a little more than 8 electron volts, which is extremely low, given the typical nuclear energy spectrum, where you typically talk about transition energies of hundreds of keV, if not even mega electron volt energy. So we are here really talking about a transition which is very special, that only has an energy of about this 8 eV, which corresponds to a wavelength somewhere around 148 nanometers. And then we say, okay, 148 nanometers doesn't sound crazy to have a laser system there and actually do spectroscopy with it. So that's the interesting part. So now it has some additional features. Like one of them is that it actually has a pretty long lifetime for a nuclear transition, something in the thousands of seconds. And that makes the line width to be exceptionally small. So we have a optically excitable nuclear state with a narrow line width, so we can possibly use this even for the development of a nuclear clock. And this is one of the main motivations behind it. So this is just like showing how exclusive thorium-229 is. So we have an energy half-life diagram. And this is the region of nuclear excited states of long lifetime. You can here see the energy scale, as I said, is somewhere hundreds of kilo-electron volts, mega-electron volts, tens of mega-electron volts here. So this is, these are not all nuclear excited states. These are only the nuclear excited states that have relatively long lifetimes, typically you call them an isomer, so lifetimes in the range of a nanosecond. This is considered as long-lived on the nuclear scale. And here, this colored region is a range where we have optical atomic clocks. And then you can see we have this thorium-229 state here, which lies in the region of the optical atomic clock. So this is just confirming that possibly it's really something where we can do precision spectroscopy with. Here's another interesting case, which is uranium-235M, which is an order of magnitude larger in energy. And what I present here is actually the radiative lifetime. So people have been discussing about, can we potentially do spectroscopy also on uranium-235M? But then if you look at the radiative lifetime of the state, you would need extraordinary large laser power. And a couple of years ago, I actually estimated how much it was, and I think you need 70 nuclear power plants to combined in one hertz line width or something. So it was a crazy number to do any reasonable with the state. So for that reason, from the energy point of view, it would be an interesting candidate, and people have frequently discussed this, but then for practical reasons, it's just like a little bit out of range. So how did this entire thorium-229 thing start? And that was back in the 1970s. Typically, people cite this 1976 year as a starting point because that was when the first paper was published on thorium-229 or the specific matter-stable state. Actually, if one digs a little bit deeper into the historic development, it turns out that this is the result of a PhD thesis that was already submitted back in 1971. So the real thing is a little bit older. And it was published by Kröger and Reich. So Kröger was still alive as a PhD person that worked at that time on this system. And what they did was they did gamma ray spectroscopy of thorium-229 higher lying states. So gamma spectroscopy of thorium-229 populated from a uranium-233 source. So if you have a bunch of uranium-233, and there is a bunch available because uranium-233 is luckily weapon material, so it was bred during the Cold War to a significant extent, so there's plenty of uranium-233 available. Just don't put too much together, so you want to have like separate. So then you can put a gamma spectroscopy setup next to it, and you do high-resolution gamma spectroscopy, and it decays via alpha decay to thorium-229, what we are interested in, but it doesn't immediately decay to the ground state, but it will decay, cascade down to the ground state via this gamma ray levels, and you can see these various gamma ray levels. And that's what they did, and they found discrepancies in what they were expecting. So there was one rotational band structure that was specifically assigned the spin level of 5.5, and they looked at it, and like they couldn't explain specific features that turned up in the spectrum. So there were gamma transitions that did decay to another 5.5 state, but not to this 5.5 state. So there were multiple small discrepancies, but multiple of them. So it turned out that there was a problem with the interpretation of the spectrum, and they figured this out. They did very detailed analysis of this and figured out and said, okay, we can explain all these problems if we assign, instead of the spin 5.5, we do the spin assignment 3.5 to it. And then suddenly all these puzzles all of them got resolved. So, and then they say, okay, this spin assignment clearly must be wrong. It must be the 3.5 and not the 5.5 spin assignment. That was pretty much settled. But then there was another problem occurring. So now they were looking for the 3.5 band head of this rotational band structure, and they couldn't find it. And they were looking for it for like a long time, but still couldn't see it. And even like gamma levels that partly would decay to the ground state and partly would decay to the excited state, so they didn't show up any splitting. So they had the best resolution of that time, and they couldn't observe the splitting. So, and then the only way they were able to interpret this is, okay, it must be a doublet, like the ground state. There must be an excited state very close to the ground state, but our spectroscopic resolution is just not sufficient to resolve it, and also we don't see the gamma ray line. So the line must be at below 100 electron volt energy. So the excited state must be at below 100 eV energy, which is already pretty small on the nuclear scale. So already this is pretty small. On the other hand, there was not a real application. So at that time, yeah, it didn't draw much attention. So it was just one other spectroscopic experiment. So there was no other group jumping onto these experiments, and they continued until they then in the 1990s, or in 1990 actually, they published the next paper where they say, okay, actually it must be very, very small. So it was pinned down to something funnily minus, like -1 plus -4. So that this was the value that they got from statistics, but they claimed in their papers, and okay, this transition must be almost certainly at less than 10 eV, because otherwise we should have seen it by now with the statistics that we have in these measurements. But it wasn't a real number, so they were only able to constrain it, but there was not a real number that they could put, like energy value that they could put onto this transition. So they continued their efforts, and then 4 years later, in 1994, they put the number of 3.5 plus minus 1 electron volt onto this. The way they did it, so this is just a part of the gamma ray spectroscopy scheme. So you can see here that there are a couple of transitions. For example, if we look at this blue transition here, so there's one, this 79.1 that goes to the ground state, and there is then this 97.13 that goes to this transition here on that level, and this goes to the excited state. So if you subtract this transition, then you should get exactly the value of this excited level. So this gap should be measured. And there are different ways you can do this in the scheme. So they at that time tried the 3, later also a 4th way of investigating this. So this was the transition measurement that they did. And now, suddenly, that they had a value of that low 3.5 assigned to it, there was a sudden significant increase in interest in the world, because this was, people realized that this was outstanding low, and also that they could do special things with it. So it was close to the time when actually the frequency comb was invented, and when optical atomic clocks arose. So there were many groups that started to work on this. So this is like a total map now. Well, I think it's not including all groups yet, but to a large extent the groups that are now interested in this. But in 2003, then Eckhart Pike realized, okay, one could possibly really do laser spectroscopy here, a unique opportunity to do laser spectroscopy on a nuclear transition. Little is known actually that Uwe Sterr was the one at that time who pointed out this transition. So he was then the one who actually had born the idea of doing the spectroscopy. Eckhart Pike was then later the one who carried out all the work, who was really the one got really mostly caught up with it. So he is in general considered as the father of the nuclear optical clock. And he published this like in some sort of low-level journal. I think at that time he wasn't expecting that it would draw so much attention. And also he said, okay, he expected that 3.5 eV spectroscopy would be a simple thing to do, so he expected to have the spectroscopy data within a couple of months. So he was assuming at that time it would just be a quick thing to do. Well, history tells different. So they were trying to search for photons emitted in this decay, but they couldn't find any photons for a long time. So there were significant efforts also from other groups to then search for this 3.5 electron volt photons emitted from this excited state. And the reason why nobody could discover any photons, that was revealed in 2007. At that time, the detector technology had improved. So there were better gamma ray detectors available with high resolution based on microcalorimetric techniques. So suddenly one could do the same gamma ray spectroscopy experiment that had been done before over several decades, but with much better resolution. Actually, so good resolution that a new doublet could be resolved, which was previously unresolved. So this specific doublet, where the 71 kiloelectron volt line decays on one way down to this 42 and then to the 29 via the 29 kilo electron volt state to the excited state, or via this state, the 7.5 plus 42.43 kilo electron volt state, and the second step down to the ground state. And so this line and this line are so close in energy, and this line are so close in energy that previously they couldn't separately resolve. So this doublet was unresolvable. But now with this improved technology, actually these individual lines were resolved for the first time, and a new energy was inferred, which was 7.6 eV. So a drastic increase of energy. So people at that time had just searched in the wrong wavelength range. So they were completely off, which explains to some part why these searches were unsuccessful. There's one even more important point, maybe, why these previous searches were unsuccessful. And the reason is that the 3.5 eV that people had in mind before are below the ionization threshold of thorium. So thorium, the neutral thorium, has an ionization potential of about 6 eV, I think 6.3 eV or something in that range. And 3.5 eV is below that, so there was not a sufficient amount of energy involved in the nucleus that could lead to a release of an electron from the shell. This effect is called internal conversion decay. So in the internal conversion decay, the nucleus transfers its energy to the shell, and then a shell electron is kicked out. And that's, of course, possible once you have the 7.6 eV, because this is more energy than you need to kick an electron out from the shell. So for that reason, people or theorists started immediately to calculate, okay, what's now with this new energy? Well, the internal conversion decay ratio that I have. So what's the ratio of internal conversion compared to gamma decay in the neutral thorium atom? And this is a large number, it's 10 to 9. So in case I'm looking at neutral thorium, it will just decay via internal conversion and not via the emission of gamma rays. And people had mostly looked in neutral thorium atoms because that was a problem that was just ruled out by the energy before. And now this really led to a slow, I have to say, a slow change of people now looking also for internal conversion electrons. Fortunately for me, this change was very slow, despite the fact that this was known now since 2007. I started my PhD in 2011, and in 2011, still people were mostly looking for gamma decays emitted. So this new information did not spread fast through the community. Yes, please.
Yeah. Is there a continuum where you have internal conversion plus light coming out?
Internal conversion plus light.
You inject some electrons from the shell, but then you also...
Oh, okay. So, I mean, what can happen is you create a hole, for example, and then an electron jumps in, and that could emit a photon, like higher order effects. That's something that could theoretically happen, yeah. Yeah, hasn't been observed. So yeah, that's pretty much where I started with my PhD. So when we started, we were in the situation, okay, this transition had not been seen for 40 years, so people were looking at it. Most of the people were looking for photons. We as well started looking for photons during the transition until I became aware, actually, that photon decay should be heavily suppressed unless you take very proper precautions. And for that reason, it might be much easier to actually look for electrons instead of looking for photons. And that's what we did, which was successful then back in 2016, so 40 years after the first indirect evidence of this nuclear excited state. And how did we do this? So we used uranium-233. We had a large, thin layer of uranium-233, and then uranium-233 undergoes alpha decay within a lifetime of 170,000 years. And this alpha decay is such a violent process, so there are a couple of mega electron volts of energy set free, and this is sufficient energy to kick one, like this thorium-229 nucleus, which is generated in this process, out from the surface. So you have this explosion, I call it, like this alpha decay, where lots of kinetic energy is set free. Most of the kinetic energy goes to the alpha particle, but still something like 80 kiloelectron volts go to the thorium nucleus, and that's just sufficient to kick it out from the thin layer. Like, it's not going through thick layers, so the layer thickness that you need here is something like 20 nanometers or something. But still, from a solid target, you can extract some thorium-229. So now we needed to handle the thorium-229 that we got there, and this was done by stopping in an ultra-pure helium environment. So we just had this uranium, which you can see here. This is this little yellow surface placed in a vacuum chamber. The vacuum chamber was filled with ultra-pure helium, typically 30 millibars or something, and then you thermalize your recoil. You call them recoil ions, the ions that are extracted here from the source. They are in a high charge state. They start in a high charge state. And what's maybe most important, in a natural way, like 2% of the thorium that is produced is in the metastable excited state. So you don't have to care at all how to populate your excited state. Nature just gives you here a natural way to populate this metastable state in the process of uranium decay. Now you stop those in buffer gas, and there are many collisions, and during these collisions, your thorium grabs electrons from the helium up to a charge state of typically 2+ and 3+. The reason is simply if you look at the release energies of electrons from helium and match this with the binding energies of electrons to thorium, and then it's energetically favorable for the electron that was previously attached to the helium to jump over to the thorium, but only to a certain level of charge state. Now the lifetime is pretty long because the internal conversion decay channel in thorium 2+ or 3+ is energetically forbidden. So it's only allowed if you have neutral thorium atoms. Once you go to the ions, you need more energy to kick one additional electron out from the shell, which you don't have because you only have this 8 eV in your nucleus available. So you can't easily kick out another electron. And for that reason, the internal conversion decay channel, which was previously causing this short decay, is energetically forbidden. So your isomer is expected to live long, which is also was then experimentally confirmed later, of course. But we were discussing we wanted to detect electrons. We thought, okay, it might be much easier to detect the electrons, but for electron detection, what we need to do is we have to neutralize our thorium. So what we first did, we purified our thorium beam. So we had a thermal, like from the thermal thorium, we just generated an ion beam, which is a relatively simple thing to do. We extracted the helium away so that we are in vacuum, so that we end up with a nice thorium beam in vacuum. Then we apply a quadruple mass separator, which permits us to filter out only thorium and decide which charge state we want to look at. So we do mass over charge separation. Why do we actually need this? Because like such a uranium-233 source is somehow, I call it, it's a little bit of a dirty object because you don't only get thorium out of it, but you start to extract the entire decay chain of the uranium. So there is uranium, francium, radium, bismuth. So there is lots more that comes out from the source. And many of these nuclei are short-lived, so they are a source of background. So you want to get rid of them. And for that reason, you have to apply a mass purification at that point so that you really end up with only thorium. And in a natural way, you can also then decide which charge state you are interested in. And now for neutralization, we just implanted it into a detector where we use the microchannel plate detector coupled with a phosphor screen. And then at that point, the thorium gets neutralized. But the neutralization triggers, of course, then the internal conversion decay. Because once it's neutralized, we know it will decay predominantly by 9 orders via internal conversion, 9 orders of magnitude via internal conversion. And the MCP detector is just designed to detect low-energy electrons. This is what the device is made for. So we then started to detect these electrons. And luckily, we immediately got a signal. So first try, we saw something. Since until 3 days before we did this experiment, I was assuming it would not work. It was just a very simple experiment for us to do. But the reason why I was really in doubt that it would work is, of course, if you have some ion, there is some ionization energy, right? So once this energy is released when it grabs electrons, when your ion grabs electrons. So you have 2+ or 3+ charge states. So the 3+ charge state sets free an energy of just from one electron of like 28 electron volts or something. So this energy needs to go somewhere. And I was assuming that this energy would lead to some release of electrons and would lead to a strong background because only 2% of our ions were in the isomeric state. Now, actually, it turns out that if you land ions softly onto such a detector surface, the energy that is set free from grabbing the electrons is just going into phonons. So that there is no signal, really, absolutely no signal. So that was a background-free measurement, which went out fortunate to us because honestly, I thought there would be more problems at that point. So yeah, that was lucky. So after 40 years, we managed to get this detection. This is Peter Tirolf, my PhD supervisor, Benedikt Seiferle, a PhD student who worked together with me on this project. So that was the big result of my PhD thesis at the end. But of course, that is more or less the start, right? Then we have for the first time a signal, and now we can start drawing all information from it. And the most interesting part for us was, of course, to get the information about the isomeric energy. Now, we didn't have photons that we could do spectroscopy with, but we had electrons. So what we wanted to do as a next step is we wanted to do spectroscopy of these low kinetic energy electrons to then draw back information to the transition energy. And how did we do this? Instead of just impinging the ions onto an MCP detector, we accelerated the ions through a graphene foil. And then in the graphene foil, the thorium ions grab some electrons, get neutralized, and then we have a neutral thorium atom beam at that time. And this neutralization process triggers the emission of internal conversion again. And in free flight, then we put this beam, or we put a magnetic bottle spectrometer around this beam, which consists out of a permanent magnet here on the bottom, and then some coil which guides the electrons to a detector which is sitting here. And in between, there are some retarding fields which allow us to then gate electrons away depending on their kinetic energy. And then you would see, ideally you would see like a sharp edge, but of course, life is a little bit more complicated, so you get some sort of spectrum here, and you can draw by calibration. So I'm skipping about some details here, but in the end, you can infer an energy value by doing the spectroscopy, an energy value of the nuclear excited state, which is what we did at the time, and this set this value of 8.28 electron volts, roughly. That was great. That was actually featured as a Nature title page at that time because it gave us sufficient information to now start doing laser spectroscopy. And yeah, this was published in 2019. If you remember, 2019 was also the year when I came here to June, and we said, okay, now we really have the sufficient information to start doing spectroscopy, which was good. But then this was only the best value that we had until 2023, because 2023, a very exciting experiment was successful, not from our group, but from a different group, where they, for the first time, managed to see also the gamma decay of this metastable state. And this is a very exciting thing. It improved, so this was the value that we had at that time, 2019. There were a couple of other values in between, which were a little bit broader, but then this work was improving quite significantly again over the value that we had obtained here. How was this done? It was done at the Isolde facility at CERN. So at Isolde at CERN, they have a 1.5 giga-electron volt proton beam available, and they hit this proton beam onto some uranium carbide target. So there were fusion products introduced, or neutron-proton capture reactions. And then they managed to do some mass over charge separation, and implanted francium-229 and radium-229 into a VUV transparent crystal. VUV transparent means that the band gap of this crystal must be very large. So for theoretical reasons, you assume the internal conversion decay must be prohibited in these crystals, which turned out to be actually the case. And so francium-229 is a beta emitter that decays to radium-229, is a beta emitter that decays to actinium-229, is a beta emitter that decays to thorium-229. And during this cascade that takes place, 13% of your thorium is naturally in the metastable isomeric state. And then they put their crystal into a VUV spectrometer, and they managed, after some background reduction, and of course there's like, it's not as trivial as I presented here, but after lots of work, they managed to see this nice line here showing up, which is a great success. So that project was led by Piet van Duppen at a time when many of us were actually in the community were in doubt that this experiment would lead to success. Simply because due to this radioactive decays, you have Cherenkov radiation emitted in a solid state environment, which leads to a tremendous amount of background. So actually suppressing the background of Cherenkov radiation to a level that you can really see this line that nobody else had seen before is really some impressive result.
Is that nanometers on the x-axis?
This is nanometers. Yeah, this is nanometers. I think this is some random intensity here. Yeah, sorry. So we had started before for doing spectroscopy, trying here at JILA, trying to do spectroscopy of the transition. And what we had tried until that day was really trying to see internal conversion electrons. So we had thorium-229 on a surface. We're irradiating the surface with a frequency comb, and we're trying to detect internal conversion electrons emitted after a laser pulse from the surface. These experiments did not work out, and haven't worked out, at least for narrowband lasers, until the current time. So this is still kind of some, yeah, I think there is still lots of work that one can proceed on. But now having the gamma decay in mind, so there were different schemes for doing the spectroscopy. And one scheme would be now, okay, we irradiate a solid state environment with the VUV laser, and then having photons emitted from the isomeric decay. So this is the so-called crystal lattice approach of doing spectroscopy with the isomeric state. There is another approach, which is the ion trap approach, where you have a single thorium-229 ion stored in a Pauli trap, and you irradiate it with laser light. And then what happens there at that, like, you have different nuclear spin states, whether you're in the ground state or in the excited state. From 5½ plus, you change to 3½ plus, and this changes the hyperfine structure of the shell. And then you can do spectroscopy of the hyperfine structure of the electronic shell. And of course, when this completely changes, you would be able to notice this while you're doing spectroscopy of the shell. So this is a concept of how you can do spectroscopy in the Pauli trap. So these are the two different concepts that we have. And we have different laser systems available. One is the high power broad bandwidth laser system, and one is the frequency comb system. So the groups that are investigating this are Eric Hudson and Eckhard Pike for this broadband approach, and Junier for the narrowband frequency comb approach. Also, there is one setup at LMU, which is still work under development. So having two different ways of doing the spectroscopy, two different laser systems, that naturally boils down to this diagram here of what one can actually do. So we have high power broadband approach, and in the crystal lattice or in a Pauli trap, and you can do frequency comb spectroscopy either in a crystal lattice or in an ion trap. So these are the, and this is a landscape of people working on this. So by today, 3 experiments were successful of doing the laser excitation, and these were exactly the top 3 experiments that I'm showing here. So Eckhard Pike was the first one who managed to see a laser spectroscopic signal back in 2024 by having a high power broadband laser source hitting a crystal lattice. he collaborated with Thorsten Schumm to get the crystals. Eric Hudson then shortly after followed up and repeated this measurement and got the same result, so also were able to excite this nuclear state. Here we were following a little bit of a different approach with the frequency comb. Also, June was able to get then crystals from Thorsten Schumm, because these were the crystals that worked best. Eric Hudson had his own source of crystals, so he had grown a couple of crystals that he got from Oak Ridge. Unfortunately, the person who grew his crystals at that time has in the meantime retired, so now, by now I think Thorsten Schumm is the only source of thorium-239 doped crystals in the world. These two approaches here are still work in progress, so they haven't been successful yet. And I will now, within the next couple of minutes, just present what has been done here with this first one. So everything was published in PRL here. This is a broadband laser spectroscopy. This is the first one in 2024 in the group of Eckhard Pike, but just into Do, and then from Ricky Elwell in 2024 in the group of Eric Hudson. So the first was what they had. They had pulse dye lasers that they overlapped into a xenon gas cell, and then in that way, via 4-wave mixing, generating the VUV beam that was required, shooting the VUV beam onto the solid state thorium-239 crystal. Then you can switch the laser off, and afterwards you expect the decay to occur with a relatively long lifetime of a couple of thousand hundreds of seconds, and you guide these photons to a detector. You want to have some filters here because you already knew where the energy was, so having some filters in the system is helpful, because at that time you can just focus on the transition wavelengths that you're interested in. And this was successful. So they managed to see the signal, and also they managed to have a first lifetime signal of this metastable state in the crystal environment. So that was the first result. It led to an improvement of the energy to this value. So we are now, the inaccuracy here is in the fourth digit. Eric Hudson did a very similar thing. The laser system was a little bit different, but in the end he was also overlaying like 2 different pulse dye lasers in a xenon gas jet environment, which generated the VUV. He outcoupled the VUV and then did shine the light onto a different type of crystal. This was this particular thorium-239 doped lithium strontium aluminum fluoride crystal. Thorsten Schumm went for a different, simpler crystal, which was just thorium-doped calcium fluoride. So that was the crystal from Oak Ridge. So yeah, and also he managed to see the line shortly after. The uncertainty was similar. So here he is quoting the 5th digit, but the systematic inaccuracy is then larger. So it's roughly the same accuracy. Now, what we could do here, and that's something that we actually developed for a completely different purpose. I told you when I started here back in 2019, we actually wanted to do spectroscopy of these internal conversion electrons because the radiative decay had not been seen. It was only seen in 2023. The IC decay had been seen, and I had been working with it for quite a while, so I felt more comfortable working with internal conversion electrons. I thought it would be the much simpler way to go with, actually. So we developed a tool to grow thorium-239, deposit thorium-239 thin films, because this is highly radioactive material, so there is no source where you can actually buy such thorium-239 thin films. So at the end, we decided we just do it our own, and yeah, we did it here at CU in the radionuclear chemistry, and I think until today, this is the only place in the world where one can do thorium-239 thin film production. It had been done one time. I did some extensive literature search. It has been done before, somewhere in the 1980s or so. So there is one, as where thorium-239 had been deposited before. But so we revived this, so to say, and managed to grow thorium-239 thin films, which we wanted to use for internal conversion spectroscopy. But now the way you do it is you cannot. So we wanted to have thorium oxide because this is supposed to have a very low work function. So we're expecting to have good electron signal from it. But thorium oxide has a very needs a very high temperature to be vapor deposited. So what we did instead, we deposited thorium fluoride, which is a lot easier to deposit, and then we did pyrohydrolysis to thorium oxide from thorium fluoride to get thorium oxide thin films. Now thorium fluoride is a large band gap material, so there one would expect to see photons emitted, and we actually did send then one of our thorium fluoride samples that were produced here to the group of Eric Hudson, and immediately they also saw a signal in the thorium fluoride environment, which was kind of nice. And so that led to some new success. But here at JILA, we had a different approach. We wanted to go for narrowband spectroscopy because these 4-wave mixing approaches, they are nice. They are very great searching tools for a first search, but they are no precision experiments. So when you want to do a precision spectroscopy experiment, you really need to have something with a narrow line width, and that's something that these 4-wave mixing, pulsed laser 4-wave mixing schemes cannot provide. So there you have like a 10 gigahertz bandwidth typically, and we wanted to have something that is a lot narrower. And for that reason, what was done here was to do like direct frequency comb spectroscopy. So we were starting up with a frequency comb in the IR. We power amplified it, coupled 50 watt into a cavity that built up to 10 kilowatt. There was injected, focused down into a gas jet for high harmonic generation. Then we were able to couple out the 7th harmonic, which coincidentally, that was also good, exactly lies in this range. I mean, it's not quite correct that it's coincidental, but we actually had to tune the laser a little bit at that time, which was some effort. So a new laser system was purchased to be tunable at that time. We shoot this light onto this calcium fluoride crystal, and again, through some filters, the photons decay to PMT, and that was successful at that time, 2024, covered by the Nature title page as well, and that improved the measurement by 6 additional digits because the technology is just completely different, right? So you really have a narrowband laser. The line width by now is probably even improved. So now the line width of the laser is very small. The line width that is observed is probably dominated by the intrinsic line width in the crystal, which is in the range of like tens of kilohertz. So these guys did actually the experiment because I unfortunately already had left back in 2022 to found, well, not unfortunately, so I was able to found my own group at that time, so I got some funding, but I was unable to join this great success here at this life. But now that this resolution was so good, also like the narrowband substructure of this system was observed, and this is exactly what you expect, because what you do is in principle Mössbauer spectroscopy. So you put your thorium nuclei in some crystal lattice environment, and then the nucleus feels the environment, surroundings, it feels the electric field gradients, and then this leads to a line splitting, which is exactly what is also observed in Mössbauer spectroscopy. So what you would expect to observe is 4 lines. What was observed are 6 lines, so one then runs into some theoretical issues. One needs to find out how to explain it, but in the end that got all resolved. So it's a very, very nice spectrum that one can obtain from this. And the person who actually led this effort was Chang-Kun Zhang, who graduated that time with 2, first author of 2 Nature papers, which is, I think, acquired some success. So now, since we are here, we can start to think about, okay, we have a blueprint of a nuclear clock, because that thing is nothing else than a nuclear clock. One can still start to improve, like here and there, can narrow things, can improve the accuracy, but we do our narrowband spectroscopy, and even comparison to the strontium optical lattice clock sitting just next to us in the lab. So that's the first blueprint of a nuclear optical clock. Now that we have it, we can start thinking, okay, what are the actual applications of that system? And there is one application that is mostly highlighted within this context, which is that such a nuclear transition is very sensitive to temporal variations of fundamental constant. Why is this? And the idea is here that actually the reason why this transition energy is so small is that there is a coincidental cancellation of high energy, like mega electron volt energy terms in the nucleus. So there is 1 Coulomb energy term and then 1 mixed nuclear structure term, and these two terms cancel each other in the nucleus and give like only this 8 eV gap that you end up with doing spectroscopy on. But if you now vary the fine structure constant is still coupled to the entire large energy scale. So you end up having a huge lever arm where like a small change in alpha would lead to a comparatively large change in this omega, so in the relative frequency, of course. And the first one who actually predicted that there must be a huge enhancement was Victor Flambaum back in 2006 already, where he did some fundamental physics calculation and said, okay, we have an enhancement factor here, something of 10 to 5, which is huge. It's a lot more than what you can have in any atomic transition because it's very special to this nuclear transition environment. And then there was some dispute. So some theorists said, okay, actually there might be no enhancement at all. Some said, okay, it's huge, and people didn't quite know. The latest estimate, and the first one that is like based on experimental evidence even, is that one recently published, 2025, says the K value is something like 5,900-ish. So there is expected to be a large enhancement factor, and this is a lot larger compared to what you have in any atomic system, and also compared to what you have in any highly charged ion system, which is the biggest competitor here. And that's great, because that gives you some guidance on like where you can do possibly fundamental physics with it. And it goes even one step further, where people have said, okay, now one could make use of this large sensitivity to temporal variations of fundamental constants also for making searches for dark matter, where the central idea is if you have like a ultra low energy extended large dark matter object, then this will lead to some drift in temporal variations of in fundamental constants. And since you have this large sensitivity gain, once you have such a transient object, it will lead to a drift in the clock frequency if you compare with another clock system, which is either less sensitive or just lies out of this dark matter field. So this has already been done. So the suggestion was back in 2014 from Derevianko. And until 2018, there were first measurements that compared already existing atomic clock data, not nuclear clock data, obviously, because a nuclear clock was developed afterwards, but one could also try to probe the same effect for atomic shell transitions, and this makes now bounds on how on these dark matter objects see. So, and how good this actually is frequently pointed out from the group of Mariana Safronova. So where I'm just citing this specific paper here, which was published, I think, in 2021, I think. So where he says, okay, a particular attention is given to the impressive ability of future nuclear clocks to search for rapidly oscillating scalar ultralight dark matter where the future projected sensitivity is presented. And this is presented in a couple of papers, and here you see like different other dark matter searches, and here's this nuclear clock search, and at least in this specific range. So it always depends, of course, on the mass of your dark matter object, but in this specific mass range, the nuclear clock could lead to the most stringent constraints on dark matter, simply due to this huge enhancement factor in sensitivity for variations of fundamental constants. So this is, I think, are the most exciting applications, fundamental physics applications. Of course, one can also think about practical ways to apply a nuclear clock really as a frequency reference. But actually what we want to do to get there is we want to have a network of robustly operating nuclear clocks, ideally, possibly even space-based, that we don't have to mess like with any of the surroundings that we have on Earth. So we need to have something that is more compact, more robust, etc. So this is now actually the point where the work starts on this nuclear clock, and one could actually do these applications. So the next goal is to have a all-solid-state CW laser for the thorium-229 spectroscopy, and this is exactly what my project in the Nucron group focuses on right now. So we want to have a laser system that is narrow band, that has a relatively large power in the mode mode, so possibly larger than this nanowatts that we are working right now, and that is simpler and lower cost compared to the high harmonic generation, which is very time consuming and also like huge and also very expensive. So the idea is developing a CW laser at 148 nanometer, and then we want to do spectroscopy in a Paul trap with this laser. This is done in collaboration with an already existing group in Mainz, where they have all this technology for Paul traps. So this 148 nanometer poses a special challenge. So the way we are planning to investigate this, or what we are currently setting up, is we use an existing 300 nanometer laser. We feed it into a cavity to do cavity enhanced second harmonic generation in a special crystal. And this special crystal is periodically pulled barium magnesium tetrafluoride. And then once we have this ready, of course, we also want to use it for doing spectroscopy. Okay, that's the application then. So we have purchased this system here, but the crystal, this BMF crystal, poses a special challenge because the crystal needs to fulfill certain requirements to be able to do some second harmonic generation here. It needs to be nonlinear, and needs to be transparent at the 150 nanometers that we need. And ideally, we have to fulfill a phase matching condition. So no such crystal exists that also fulfills a phase matching condition, but we can circumvent this by doing periodic polling, so by doing quasi-phase matching. And BMF is, I think, the only crystal that is available that has the three conditions. It's nonlinear, it's transparent, and it is ferroelectric, and in that way also permits periodic polling of the crystal structure. So that's the reason why we started working with this crystal. And we already have the crystal available. It's transparent. We have done, in collaboration with Fraunhofer IPM, some periodic polling of these crystals. Unfortunately, these polling structures, in the beginning, we were very excited when we saw this here and thought we had 2.5 micrometer polling period achieved, which was exactly what we wanted for our experiments. But then it turned out that was just a surface effect, and it didn't pull through. So what we have achieved right now is something like 7 micrometers. So we are still working on pushing this down. But with the crystals that we have, we were able to already do some first tests of SHG. And yeah, I haven't prepared any slides for it, but I can maybe tell you that we have seen first SHG signals from the crystal. So we have a CW laser at the 148 nanometer laser now available, but the powers are fairly low. So we are still in the process of increasing the power. And we hope that within the next couple of months, we will get sufficient power to actually be able to do some spectroscopy, to really do some physics with this laser system. So that's a good thing. This is an overview over the entire thing that we are still in the process of setting up in Mainz. So we have the Toptica 300 nanometer laser, then the cavity, which generates the 150 nanometer light. We have a BMF crystal in this cavity, which we obtained from IKZ and IPM. So this is a collaboration that we set up. And now we are still in the process of setting up a power trap system where we want to do sympathetic cooling of the thorium-229 3+ in the power trap. We extract thorium-3+ from a buffer gas stopping cell, just like the way we did it in the work back in Munich, extracting it from a uranium-233 source. Alternatively, we can also use an ion gun. And then once we also have a frequency comb locked to the fundamental, then we can really run the spectroscopy experiment. So this is a rough overview. And with this, I would like to thank you for your attention. So these are the funding and collaborations that we have been working on. Many people to work in collaboration with in the past. And that's a picture of my group. So we were 7 people working on this right now, 8 with me. Thank you so much.
Great, thank you, Lars. We have a few minutes for questions. Are there any questions in the audience? Yep.
So in the beginning, you talked about thorium-2+. And so what's the ionization energy there?
Ionization energy from 1 plus to 2 plus, or from
No, 2 plus to 3 plus.
2 plus to 3 plus is 28 EV.
Okay, but then why are the lifetimes you were quoting so short, just 1 second, rather than sort of more native ones that are 1,000 seconds? Why is it so short-lived?
So I don't know exactly which lifetime you are referring to.
You
So
had
the-
like a
so
1 second lifetime in the beginning?
No, it's longer. So
It's way in the beginning.
Here are signals.
No, it was in the very beginning where you showed the
So okay.
progression from uranium to
Yeah,
33.
we have to distinguish between whether we are in the nuclear thorium atom or whether we are in the. Oh, okay. I think I know what you are referring to. So maybe there is a little bit of a confusion.
Yeah, this
You're
one.
referring to this.
You have the
So,
the thorium 2 plus as a.
Yeah,
Is
that
that
should
1
be
second?
that should be a minute here. Sorry, I think
Oh, okay.
the
Thank you.
unit is missing here. So
Okay, that explains.
that's larger than 1 minute, and we were at the time unable to. So we were trying to see how long the lifetime would be by just keeping the ions stored in this radio frequency quadrupole, but then we were not clean enough because there were some like buffer gas backgrounds and so, and then we lost ions. And for that reason, we only could put a lower limit. So we knew it was larger than 1 minute. And here, this is when you trigger the internal conversion decay signal. This is 7 microseconds.
A reminder to everyone that units are important. Other questions? Yeah, up there.
Is there a prospect? Very nice talk, thank you. Is there a prospect to do the clock also within a solid state media, or is it the reason why everybody's pushing to do it in the ion trap to have not this electric field that splits your line and so on? Or can you maybe give a bit more?
No, there's great prospects also for doing the nuclear clock in a solid state. So the two schemes that I gave here are really the ones that are mostly followed. One could even think about a surface approach, but that has problems right now. But these are the two approaches that are followed. And here you can imagine you have a huge statistics. So here you irradiate not a single nucleus, but here you irradiate like 10 to the 10 nuclei in parallel, which can lead to a tremendous advantage in statistics. So you can get a great stability. At the same time, of course, you have to cope with the environment because your transition frequency will feel, for example, the temperature and the entire environment. So for that reason, you somehow have to get your environment sufficiently well under control. But once this is under control, that thing has a great prospect for a nuclear, being a very practical device also as a nuclear clock, because it's a very compact and easy thing. You don't need to have any trapping. You don't need to do any laser cooling. You just naturally you put your crystal somewhere and you shine light on it, and that's your clock. So it has drastic advantages, but it also has, so it's less complex, but it's also, there is more coupling to the environment. So in the end, there are pros and cons for both. I think it's interesting to investigate both systems.
Maybe just a follow-up question, if it's okay. Do you have some idea of what kind of precision one would need in the solid state environment to actually come to a regime where you start to really use the enhancement that you mentioned before for the test of fundamental constant? Mm-hmm. Is there some threshold that you need to have in precision such that you can compete with other experiments?
Mm-hmm. I'm not. So I would need to look into the papers to give a secure answer to that question. If I remember correctly, since you have this enhancement factor of 10 to the 3 somewhere, that gives you already a good start, so to say. Now the best clocks that are now operating at the 10 to the minus 18, 10 to the minus 19 level. So if you are here at the 10 to the minus 16 level for that clock and use this additional lever arm of 10 to the 3, then you have something that is comparable. Now this is not fully accurate because also there are enhancement factors involved in the atomic shell transitions. And then you need to look really at the specific transitions that you have, and I don't know exactly what the best limits there are right now. But I think you can relatively quickly get competitive with at least what has been done now with ordinary atomic clocks. And then, of course, the goal would be to push this further. Yeah.
All right, I think in light of the time, let's hold any further questions till afterwards, but let's thank Lars again.
Thank you so much.